Alright, this is the master video for Chapter 8, Sections 1 and 2. This video we're going to talk about not actually solving a system of equations, but how can you model a system of equations, or just an equation for that matter. So just take this example right here. Trevor and Lara have a combined age of 58 years. Okay, well, that's not a mathematical equation, but we can represent this statement that's just written in English mathematically. So that's what this video is about. How can you translate from English to math? So it says convert each statement into a mathematical equation and assign appropriate variables to each unknown quantity. So here we have Trevor and Lara, and they have a combined age of 58 years. So the unknown quantities are their ages, but we know that their combined ages, meaning when we add them together, we should get 58. So we're going to let Trevor's, put an S there, Trevor's age equal T. So every time you see a capital T, we're just talking about Trevor's age. And we're going to let Lara's age, you can call it whatever you want, but it probably makes sense to use L. So having a combined age of 58 years, that's easily written mathematically as T plus L equals 58. So there you go. English, math. Next, a water tank initially containing 65 liters of water slowly leaks at a rate of 5 milliliters per minute. So every minute that goes by, 5 milliliters of water leaks out, and the container, at least in the beginning, has 65 liters of water. So over time, this number is going to go down. All right, so how can we model this using an equation? So let the volume of water. Okay. Now we have to be careful with our units, because here water by volume is given in liters, but here the rate at which it's leaking is in milliliters. So when we use these numbers in our equation, we have to be consistent with our units. So I'm going to choose to stay in liters. So let the volume of water in liters, I'm going to let that equal V. Okay, so every time you see the letter V, that just represents how much water is still in the container in liters. The other unknown quantity, well, that's how much time has gone by. Okay, what are the units of time? Well, it's only mentioned once here in minutes, so I might as well keep it in minutes. So let time in minutes equal T. So let's take these two variables and put them in the equation. Okay, well, we know that the volume of water begins at 65, because we're told initially, which means time is equal to 0, that there is 65 liters of water. Now we're just setting up an equation with variables in it and numbers, so we actually don't want to put the units here, so you should not put an L here. Alright, so over time, what happens to this volume? Well, it doesn't stay at 65, it decreases, because as time goes on, as every minute passes, we lose 5 milliliters. Well, we can't just say 5 here, because that would be in milliliters, and we have to express that in liters. Okay, well, there are 1,000 milliliters in a liter, so if said differently, that means 1 milliliter is 1,000th of a liter. So there's 5 of them, so this is minus 5,000ths of a liter. Okay, so at least these are now both in liters. But we're not quite done, because this is just a constant. It has to change with time. Okay. So this is our volume, but this is not the volume, this is a rate. Okay. We need to multiply this by T. Why do we need to do that? Because this quantity right here, okay, the 0.005 times however many minutes have gone by, that tells you how much water by volume has leaked out. Okay, and that is what gets subtracted from the 65 to tell you how much water remains. Okay, so a little bit trickier, but hopefully you get the idea. The temperature of a liquid decreases from 68 degrees Celsius to 62 degrees Celsius in 3 minutes. Okay, so the two unknown quantities are, well, time and the temperature of the liquid. And we are told that in 3 minutes, its temperature will decrease by 6 degrees, okay? Because 68 take away 6 is 62. So let's see if we can model an equation for the temperature of this liquid as time passes. So let's let temperature now there's only one unit of temperature given, but in degrees Celsius, I'll let that be capital T. And let time, okay, here, let's just be consistent here, time in minutes, we'll let that be little t. Okay, so let's see what we can come up with. Okay, so to construct the equation we're looking for, we can actually use the previous example as a bit of a guide. Here it says 5 milliliters per minute. Okay, per minute, that is what we call a unit rate, meaning it tells us what is the change for every 1 minute that passes. Well, we are told that our change is a decrease of 6 degrees, but not in 1 minute, in 3 minutes. Okay, that is not a unit rate. Okay, so if we want to use this as a guide, we need to express this as a unit rate, meaning what is the change for every 1 minute. Okay, well, it's actually quite simple to do mentally. If I change by 6 degrees in 3 minutes, that means I change by 2 degrees for every 1 minute. Okay, and if that's not clear enough, you can actually just write it out. So if I decrease by 6 degrees for every 3 minutes, okay, we know that numerically, -6 over -3 is just -2. And our units are degrees Celsius per minute. Okay, so this is now a unit rate. This is how much the temperature changes for each minute that passes. So now we can construct our equation just like the previous example. So T equals where we start, so that's 68 degrees. And we're decreasing, of course. So this is minus 2 degrees per minute times however many minutes pass. Here, I'll put this one in red. Okay, and you can check this. Okay, does it work? Okay, so after 3 minutes, this T would be 3. So 68 minus 2 times 3, that's 68 minus 6, which is 62. Okay, and that makes sense for what we have here. Okay, but you could use this to predict what would the temperature be after 4 minutes, or 5 minutes, 6 minutes, etc. So that one's a little bit trickier, but hopefully you get the idea. Practice makes perfect. All right, put some finishing touches here. So when you're writing an equation, you don't put units in there. If you're evaluating an equation, then you can, but we're not doing that right now. So there we go. Next, we're going to move on to modeling systems of equations. So it's what we were doing before, but the previous problems, we couldn't create a system. We were only able to create one equation. So for instance, in this problem, 5,643 people attend a concert at $15 per adult and $12 per child. The total ticket revenue is $79,059. for all of this information written down here, we can create not one, but two equations. Hence, we will have a system of equations. Okay? And you may notice that, well, there's a piece of information that we would likely want to know, and that is how many adults were at the concert, how many children were at the concert. We know how much each of them have to pay, and we know how many people were there in total, but we don't know how many of each age group. So we're going to let the number of adults equal A, whatever A is, and we're going to let the number of children be C. Okay? All right. So the first equation is right here. That's pretty easy. 5,643 people in total were at the concert. So that just means the number of adults plus the number of children is equal to 5,643. Okay, that was pretty simple. The next equation, of course, has to do with the amount of money brought in, so the ticket revenue. Well, we don't know how many of each age group were at the concert, but we know how much each of them has to pay. Okay, so one adult has to pay $15. Well, A adults would have to pay 15 times that. So 15A, or 15 times A, this quantity here tells us how much money was brought in total by adults only. Okay, because that's $15 per ticket times the number of adults that attended. And similarly with children, $12 per child times the number of children, and when you add those together, we should get the total ticket revenue. So that was $79,059. Okay, we are done. We are not asked to solve the system, to graph the system. We just wanted to model it, meaning just translate these two sentences in English into two mathematical equations. You could try and solve these graphically, but these numbers are quite large and, well, good luck. I'll leave it at that. Trisha is 5 years more than twice Chris's age. In 7 years, Trisha will be 2 years less than twice Chris's age. Now, that seems probably ridiculously complicated, and to try and solve that just by riddling numbers out in your head, well, I would get frustrated very quickly. Okay? So this is how creating a system and modeling things mathematically can make this, which seems quite ridiculously complicated, can actually make it quite easy. All right? So after we gather ourselves and we stop crying, because the problem seems so hard, let's look at what we don't know. Well, we don't know how old Trisha and Chris are. Okay, so let's just create two variables. So let Trisha's age, well, we're assuming years, equal t. And then we'll let Chris's age be C. Now we have to be careful because the problem actually has two time frames. This one is in the present and this one is 7 years in the future. Okay, so when I say let Trisha's age be T, we just need to be careful, are we talking right now or are we talking in the future? Okay, so let's just make a note of that. This is now. Okay. Why do I have to be careful? It's because if I refer to Trisha or Chris's age in the future, I can't use T and C. I would have to use T plus 7 and C plus 7 because however old they are now, they will be 7 years more than that, 7 years in the future. Okay. So let's look at the first sentence. This is present tense. So this says Trisha is 5 years more than twice Chris's age. That's actually very simple to model. Trisha is 5 years more than twice Chris's age. So we're just taking twice Chris's age and we're tacking 5 years onto that. So you could say 2 times c plus 5 or 5 plus 2 times c. There we go. Okay, so here's this sentence in English modeled mathematically. The next one is a little bit more challenging. Okay. In 7 years, Trisha will be 2 years less than twice Chris's age. So in 7 years, Trisha will not be t. She will be t plus 7. Because t represents how old she is now. So in 7 years, Trisha will be, so will be is the future tense for is, 2 years less than twice Chris's age. So we take twice Chris's age and we subtract 2 from it. So here is the common mistake that people will make. Twice Chris's age and then we take 2 years off. Can you see where my mistake is? Well, I hope you do. I used c incorrectly. Because I'm in the future, c, well, this actually represents his age in the past. So whenever I refer to Chris's age in the future, I have to add on those years. So this is twice Chris's age in the future, and Chris is now c plus 7 years. Okay, so that's double his age in the future, and then we subtract the 2 years. Okay, so we're not interested in solving this system. We will down the road, and to do it algebraically is actually very simple. Okay, it's a lot easier to try and solve this algebraically than it is to try and riddle out these numbers in your head. Okay, but all we're trying to do is model the system. So we are done. A person can buy 2 drinks and 4 snacks for $9, or 3 drinks and 3 snacks for $10.50. Okay, so if you read this, what is obviously missing is the prices of each item. So we don't know how much snacks cost, and we don't know how much drinks cost. We just know what certain combinations are when we add them together. So let's let the price of one drink be, I don't know, D. You can use little d, uppercase D, doesn't matter. And let's let the price of one snack be S. If you're ever using S as a variable, nothing wrong with it. Just be careful that it doesn't, by mistake, become the number 5. All right. I've done that a few times. Okay, so 2 drinks and 4 snacks. Well, this is actually, I would argue, easier than the previous ones. So 2 drinks, so 2 times D, that's the price of 2 drinks, and 4 snacks. Okay, so that's the cost of 4 snacks. When added together is $9. Wow, that was easy. Or the other possibility is 3 drinks and 3 snacks is $10.50. So without any units, that's just 10.5 or 10.5. Okay, so we are done, because all we want to do is model this using a system of equations.